I want to talk today about inductance, inductors, and back EMF. I always try to find analogies for some of these things, and this one's hard when it comes to finding analogies, because I think every year I kind of believe you guys have enough mechanics information to be able to make a mechanics analogy, but I find that really doesn't work anymore. That the mechanics stuff feels very separate from here. But there's a certain way that I think these things work. And a lot of the times in circuits, we don't see the connection that there is between, say, something we learn in mechanics and something that we have in electronics. But circuits have inertia. And it's not inertia like we see with mass and like Newton's laws, but there is a certain inertia. And it's hard to see it, but it shows up. We tend to say that things happen instantaneously in circuits, right? We've closed the switch, and in your circuit, there's an instantaneous electric field that applies to all of the electrons all at once. Trying to find a way to express that, like, are we violating some rule? Like, isn't that going faster than the speed of light? Well, no, not really. Because the difference here is that we're not talking about actual masses moving fast. We're talking about an electric field being established in a region of space. In this case, the region of space would be the wire. So at the very beginning of the year, I tried to indicate that when you close this, we have an instantaneous current everywhere in the circuit all at once. Well, it was a bit of a lie. It was not a lie because I was trying to deceive you. It was a lie because you weren't prepared for what really is happening in a circuit. Now, if I had done my normal discussion, which I don't remember if I did or not, because this would be back in November, I would have talked about how you should imagine that this is like a tube and it's filled with little ping pong balls all the way around the tube that's completely filled with them. So that when you push one in one side, they all move at the same time. Right? That was the analogy I tend to try and use. That it's not light speed. It's that they're all in physical contact, which is largely a false assumption. They're not in physical contact. But all of the electrons are repelled and spread out in the circuit before you close the switch in such a way as to reduce any point where one force would be greater than the other. That's why they spread out on the outside of the wire, or why they spread out on the outside of a conductor, or why they always displace themselves so that the electric field inside is zero. And so when you move one electron, they are all affected. But there's more to the story, and that's what I started with yesterday. The idea that when we do first close this switch, and the switch is instantaneously closed, we make that connection. Well, the moment the connection is made, we begin a current. And we would say that current would be instantaneous, and we would say it's something like this. However, the moment we do that, we establish a magnetic field. And that magnetic field is based on the direction of this current in the loop, which is going to be this way. That's the direction of the current in that loop. And when we do that, the magnetic field would be into the loop. This is a closed loop. It has an area. This is a change in magnetic flux. And even though this change in flux is caused because we closed the loop, because we created a loop of current, that change creates in the circuit what appears to be another EMF somewhere else. And I'm drawing it like it's a battery, but I'm purposely drawing it that way to emphasize that this is being created due to Faraday's law. An EMF in the circuit that's attempting to prevent the establishment of the current. And this is known as a back EMF. This is the simple term for it. But what it's also known as is self-inductance, that there is an induced EMF created because we started a circuit. Now, this isn't going to be very big. There's not much flux here. Even if it's a very large current, a very large magnetic field, we don't have lots of loops of wire or anything like that. But what we do have is something that's going to prevent the establishment of this current, or at least try to. This idea of self-inductance has been established as a measurement, an EMF, in the same way that we have an EMF for capacitors. And we would say that that's going to be Q over C, the EMF for a capacitor. We have a way of stating this EMF. And you have to understand the statement of this EMF is going to be a little bit more complicated because it has to do with the rates that things are changing in the circuit. So first, we define inductance or inductors with a capital L. We'll call this the inductance. Capital L. And there's a whole lot here that you're not going to like because it's not a capital I, it's a capital L for inductor. Don't get me started because the unit of inductance is the Henry as well. And when you start seeing the unit, you're going to be like, I don't know, just stop trying to make sense of it. I don't even know who Henry was. That's how low on the old totem pole all of this is. But inductance is a little interesting. It is L times di dt. So there is a back EMF created in a circuit, and it is based on the rate that the current is changing. And we call this measurement an inductance. Now, obviously, this circuit would not have very much by the way of inductance. In fact, the inductance would probably be so small as to be unmeasurable. So if you wanted to ramp up the inductance, if you wanted to make this something that would be measurable, there's probably a pretty simple way to do it. We want something where any change in current would be amplified by a system that would propagate, perhaps, or not propagate, amplify that change in current. What we want is something that would have a lot more magnetic flux. So an inductor is just a coil of wire that you place in a circuit. An inductor has all the things that would create way more self-inductance and back EMF. Because we have coils of wire, the current in those wires are going to try and create a magnetic field through the center of our inductor. And of course, that's going to be fought by this back EMF because you're trying to create a magnetic field in a space that did not have one. And because you're doing that, there's going to be an EMF created by Faraday's law to try and prevent the establishment of this current. So an inductor circuit, and we'll put a resistor in here to either represent the resistance of the inductor itself or an external resistance in the circuit. So this is what a basic inductor circuit looks like. Now the truth is all circuits are inductor circuits. All circuits have a certain amount of back EMF. But you can buy an inductor, which is just a solenoid. That thing that's sitting on the desk up there, that's an inductor. And an inductor on its own has properties that are related to like the way a capacitor works. You see, this back EMF attempts to prevent the establishment of a current. Attempts to prevent. Now, I want you to think on this for a little bit. It attempts to prevent. It works in the same way that a capacitor kind of worked. You get the maximum amount of back EMF when the current is changing the fastest. That's why the back EMF is max the moment the switch is closed. there was no current, and suddenly you're imposing a current on the circuit. That sudden change creates the greatest amount of back EMF. But once current starts to flow in the circuit, the rate of change of current goes down, and therefore so does the back EMF. So the longer the switch is connected, the less back EMF there is. This is the reverse of what we see with a capacitor. In a capacitor, when we first close the switch, we get the maximum amount of current because the voltage across the capacitor is 0. So we get all the current. And then the current slowly decays over time. This is going to be the opposite. In this circuit, we're going to get a huge back EMF the moment the switch is closed. But that back EMF is going to decay over time, and so the current's going to start at 0 and then ramp up gracefully to its maximum. Now, I want you to imagine right away the kind of benefits having an inductor in line with your circuit gives you. Right? It gives you the ability to ensure that you don't hit any of your electrical components with a massive amount of current right at the front end of turning something on. Putting an inductor in your circuit is a surefire way of helping to maintain a slow rise of current. And also, you can imagine that it would do the same at the end, right? It's going to try and hold on to that current at the end. Inductors are interesting devices. They have some uses, and we're going to see several of the uses of inductors in circuits. They're another physical device. So like a capacitor, an inductor is something that ramps up magnetic field, while remember, a capacitor ramps up electric field. Most inductors are nothing more than coils of wire. That's really almost all they ever are just coils of wire. Oftentimes they'll have an iron core in the middle of them, so they change mu naught into something that is bigger, so they get more bang for their buck. Just like we have a dielectric inside a capacitor, we'll have a core inside an inductor. Tuesday, we're going to do an inductor lab, and I've got a whole bunch of actually really large inductors. The problem with inductors that is dissimilar from capacitors, and what makes a real inductor more difficult to work with, is inductors usually have a lot of wire involved because we're talking thousands and thousands of loops of wire. Because of that, inductors almost always come with a lot of resistance. A capacitor didn't have any resistance on its own. It was just an air gap, right? One plate next to another plate. But an inductor adds resistance to a circuit, and sometimes it adds a substantial amount of resistance. So although I've drawn a resistor here, most inductor circuits, the inductor is the resistor or acts as a resistance. So you can't just add an inductor without also adding resistance to your circuit. In a capacitor circuit, you just throw a capacitor in your circuit, but you have to account for the resistance of an inductor if you're trying to make a real circuit. You guys follow what I'm trying to say that? So the reality of an inductor and what we're going to talk about in an inductor are different things. Because the reality is we're assuming this inductor somehow is using magical resistance-free wire, and that the resistance is separate. But that's not how real inductors work at all. So I want to start out by recognizing that this circuit has all the same qualities that we've seen in other kinds of circuits, in that when we close the switch, we create a closed circuit of which our Kirchhoff's rules apply. The circuit's going to have a voltage supply and 2 voltage drops. This inductor circuit is clearly going to be, on its own, a differential equation. Right? I don't have to replace anything with a differential. The definition of an inductor is already a differential. Oh, and by the way, I didn't say this already, but dIdt is amp seconds, or amps per second, and the other side is voltage, so an inductor is volts per amps per second, or a volt second per amp. Again, don't try and make heads or tails of that, but that is a Henry. And just wait, you can also express Henrys in terms of Tesla. I would say I'll leave that to you as an exercise, but even I know that that's punishing. We'll look at the 2 different ways you can measure Henry, but we measure them in Henry. A 1 Henry inductor is huge. It's like a 1 farad capacitor. So just like farads are fairly big measurements for capacitance, henries are big measurements for inductors. Being that I thought I was a smart guy, I bought a whole bunch of 3 Henry inductors for an experiment because I thought it'd be nice to be nice and big. We'd be able to see nice slow transition of current. They are completely useless because each one of them weighs about 2 pounds, so they're heavy because it's just a big box of iron, and they add so much resistance to the circuit that they're almost unusable in any regular circuit. You can't light the light bulb or anything like that to see any kind of transition because they are so much more resistance than even the light bulbs. No current ever really passes that's measurable enough to light up a light bulb. So we're going to try the lab using LEDs and just use the resistance of the inductors as our experiment. The LEDs will light up, but we're going to try and do standard LR circuits like we're going to see here tonight. So this solving of this differential equation, I don't think I have to do it, right? You guys are good at this now. So I'm going to stop talking, which I know is unusual. I'm going to say you guys do this because we just did it yesterday or day before yesterday for the RC circuit. It is the exact same thing. But what you're going to come up with, I guess we're not going to do it. What you're going to come up with is an expression for current as a function of time. Okay? Don't disappoint me. Try and do that and have it done by Tuesday.